Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to do a really fast review of safety. You've had a course in that. We've been doing safety moments all semester long. I just want to give you one last chance to think about how safety analysis ties into what you need to write up for your report. So we'll start with risk assessment. OSHA keeps records of all industrial incidents and then reports them. And we've got some data summaries in our book and table 26.1. The incidence rate is the number of lost work incidents per 200,000 hours of exposure. And the fatal accident rate, or the FAR, is the number of deaths per 100 million hours of work. And the fatality rate is the number of deaths in a year per total population risk. And so you can, look at these various things and it's like, okay, rock climbing to me sounds very scary, but frankly, traveling by car causes more deaths per year, than rock climbing. But for a number of hours of doing it, rock climbing is much more dangerous. So these various numbers give you different views of the risk of these activities. When you use this, usually you kind of play a game of worst case scenario, and you think of all the worst possibilities and how they could interact to cause potential disasters. And each one of those has a statistical risk, and you multiply and add those values appropriate to how they could interact, to find the net risk of various failure modes. Another thing is safety data sheets, and we've been using these, but we haven't specifically discussed them. So the information that's on a safety data sheet is going to be the material and the manufacturer's identification information, what's hazardous in the ingredients, and identifying information with physical and chemical characteristics. So, it's a yellow powder or it's a, lightly colored liquid, something like that. You'll have fire and explosion hazard data, reactivity and health hazard data, and then control measures and precautions for safe handling and use. Do you need to wear a ventilator, or can this just be done, wearing gloves, etc.? There's also a lot about EPA that falls under safety, because when we are talking about safety, it's not just about protecting ourselves and our colleagues that work with us, but also the public and the earth around us. And so the EPA is the body that regulates emissions from process plants, and we have the planned emissions, things we know that we're going to be releasing. But we also have fugitive emissions, those little sneaky leaks, Control valves, they leak all the time, And we have emergency emissions when things just go badly wrong. And we need to be able to think and plan for all of those. Now, the categories that normally we're most concerned with are the volatile organic compounds, or VOCs, and the hazardous air pollutants, or the HAPs. And the risk management programs are going to be a hazard assessment, and then you need to have prevention and emergency response measures. Fires and explosions are one of the, very serious problems that we need to worry about as chemical engineers. And so this here is just a list of vocabulary. So combustion is the rapid oxidation of a fuel. The auto ignition temperature is the minimum temperature where the combustion will be sustained even if you don't have a heat source. So if just it's that hot. The lower flammability limit, or a lower explosive limit, is going to be a composition of fuel to air that's going to support combustion or explosion, similar with an upper limit on these, which is the maximum composition. So you can have a fuel that's too lean or too rich to be flammable. And then the flash point is the temperature where the vapor is in equilibrium with the liquid pool at standard pressure. an explosion is very rapid combustion, and so rapid that it forms pressure waves that actually propagate the combustion. All chemical engineers should know how to calculate an adiabatic flame temperature. So to do this, you're just going to write an energy balance, and you set the heat transfer and work equal to 0. Now, when you write this expression, don't forget to include the heat of combustion. It's going to be a flame temperature. And then look at the change in enthalpy from the original feed temperature to the flame temperature. Now, we don't know what that is. It's going to be the final T that we're solving for. And use the integral of C sub P dt with this final flame temperature. And then you're going to solve for the value of T that makes this true. Now, I like this graph here because what it shows is that this is the stoichiometric combustion amount right here in the center. And as you add excess air, right, the oxygen level is going to go up. If you add excess fuel, you clearly will not have any oxygen, but you will have fuel that remains. And carbon monoxide is going to be preferentially formed when you have not enough oxygen and decrease as you increase the amount of excess air. But the efficiency of our flame is sort of a combination of all of these factors, and it's going to be someplace slightly above the stoichiometric combustion temperature. So when we way back in our mass and energy balance days, remember we typically were saying, well, 20% excess air. Why? Well, because that's going to put me over here to the spot where my fuel is consumed completely, where I'm creating a minimum of carbon monoxide, and that's going to be peak efficiency. Okay. Now, the reason you don't want to add too much additional air, right? You want to burn all the fuel, but you don't want to have so much extra air that now then all you're having to do is heat that extra air. And so that's what's lowering our efficiency here. This is a sample problem that I found that was just nice as a reminder of these are your equations here that you're looking at the entrance and the exit, the enthalpy with the heats of formation, right? That's going to get your heat of combustion. And then doing this with the C sub P values for this mixture that they had here. And they did this and they got a flame temperature for their fuel of 899 Kelvin. I didn't give you the full problem, so don't worry about the details. But that's the idea of what you need to incorporate. So you're going to need C sub P data, you're going to need heats of formation, and basic enthalpy data. Now, a lot of times for common fuels, you can look up the higher heating value and lower heating value for those fuels. And a higher heating value is the enthalpy of combustion when all of the water forms a liquid. So water's formed in a combustion reaction. If it is a liquid, then you have the higher heating value. If it is a water vapor, then you have the lower heating value. And so those values are shown over here for a couple of items. But this is just a basic table of data that you might find. But that's helpful because that allows you to very quickly calculate how much energy you can get out of a combustion reaction. I'm going to post these slides in our class Canvas so you can look at this video on your own. But there are a lot of different issues with explosions. You can have vapor cloud explosions, dust explosions, BLEVs, runaway reactions. There are so many of them. The link I have here is, I think it's a very good video to show you a BLEV. And then we need to be sure that we're including pressure relief devices. So there are safety valves and relief valves and pressure relief valves, and they're not quite the same thing. It depends on whether what you've got inside the vessel is going to leave as a liquid or leave as a gas or leave as a two-phase mixture. But for our purposes, we can call them all a safety relief valve. But you frequently put these in combination with rupture discs. Okay. You do this because that protects, you put that in first before the safety relief device so that it protects the safety relief device from unnecessary strain. Okay. We want it to work properly when we ask it to. Now, where are you going to need to put these various safety relief valves? Every vessel is going to require one. So when I see your final drawings, I want to see a safety relief valve on every vessel. Any section of liquid-filled pipe that could be blocked in, because those liquids could heat up to become a vapor. And so any section that has valves on either end of it in some way, if it could be blocked in, it needs a relief device. On the discharge side of positive displacement pumps, compressors, and turbines, and everywhere you have a steam jacket on a vessel, you're going to need a relief valve on that. Now, you guys have been doing a really good job on your designs, on the process hazard analysis. This is another what-if game, and you look at this in different ways. And I've seen two different styles you guys have been using. But you can do failure mode and effects analysis, a fault tree analysis, hazards and operability study, a hazards analysis, a HAZAN, lots of different things to do there. And most of you have been choosing the HAZOP. To do a really full HAZOP would probably take a dedicated week. And knowing more about the details of our system than we know right now. But you start by identifying what's the normal operating condition and then look at all the possible deviations. So you have flow going in. What if I had no flow? What if I had more flow? What if I had less flow? What if I had some different combination of chemicals in that flow? Okay. Now, for each of those possible deviations, I want to think of the cause, the consequence, and what action should be taken. And here is a little sample from your book. Now, there are a lot of acronyms, and I've just included these in the slides simply so that you'll have a place to look them up when you're like, what is that? There are just a large number of these. And I don't even think this is a very complete list. But this is just simply included here so you have it as a resource. So this concludes this lesson. And in our next lesson, we're going to be looking at sustainability. Thank you very much for your time.